Across the world, up to about 150,000 women each year die post-childbirth due to bleeding, many or most of whom would be saved in those countries if there was a safe and sufficient supply of blood. Across the United Kingdom, we use around about 2.5 million blood components each year. Today in the United Kingdom, blood is donated by normal, healthy members of the public. They obviously undergo quite a stringent selection process and also undergo testing for various kinds of viruses to ensure that the blood is safe. The blood is then processed and the red blood cells are stored for up to about a month in a refrigerator in case of need for use. Cultured blood would potentially provide us with a number of advantages, not just in this country but across the world. Firstly, in that it would provide a ready source of blood and a sufficient source of blood. Secondly, of course, that it would be infection-free. And thirdly, that we would make blood which is of a near universal donor type, that is group O rhesus D negative, which then therefore would be able to be given to the vast majority of people very safely without necessarily extensive testing.
We're the basic biology lab within the Wellcome programme, so we're actually developing the methods to differentiate the cells into red cells. We are taking human embryonic stem cells, which are a unique stem cell population, so they're derived from a very, very early stage of the embryo, and because of that they have the capacity to make any tissue in the body. What we're able to do is to try and coax those cells to turn into blood, and to do that they have to go through multiple stages of differentiation, which is the maturation process. And then once they've decided to be blood, there's many different types of blood cells, so now we have to convince them to be red blood cells and not white cells, for example, or platelets. And then finally we have to get enough of them, so we also have to make sure that they continue to proliferate at all times so we can get large numbers of cells. And we do all of this using growth factors and cytokines, which are molecules which are found in the body naturally, but we understand how they signal to the cells to make them make decisions. The whole process is about 35 days. Roslin cells are deriving the embryonic stem cell lines at this good manufacturing process grades that can be used for clinical use. And then they give us some that we can bring into our lab and use at a research grade. So we're then making the protocols, then we tell them how we've done it, and then they try and do it in a way which is clinically acceptable.
Well, the current project, which will continue over the next 2 years, we're hoping to be in a position to generate enough red blood cells to do animal studies and early studies in man. I think we're still probably a good 5 to 10 years away from generating red blood cells for routine clinical use.
If we're going to successfully either contribute to or replace donor services at some point in the future, the biggest challenge is the cell numbers, just having physically enough blood. Each bag of blood has 2 million cells in, and we're going to have to make 2 million bags of that a year.
Well, I think the direct impact of this project, if it's successful, is that it would simplify blood transfusion in this country, and it would enable blood transfusion in many countries across the world which currently are not in a position to provide a safe and secure blood supply. But more broadly than that, I think a lot of lessons that we learn from generating red blood cells will be transferable to the generation of nerve cells for stroke repair, or heart cells for heart repair post-heart attack, and so on and so forth. So I think this is just the first step on what's likely to be a very long but exciting journey.